Hello, in this lecture we will find the radius of the small circle. In the drawing we have two circles with an internal length between them and this point. Let's define this point as point N. And we know that AB is the diameter of the big circle and AC equals to 9 units and BD or DB equals to 4 units, and this is a right angle and this angle also equals to 90 degrees, and we want to find out the radius of this small circle. Okay, first of all let's define the center of this small circle as Q, or point Q is the center of the small circle, and we will define the center of the big circle as P. Point P is the center of the big circle, so I will write it down. That point P is the center of the small circle, and point Q and point Q is the center of the small circle, and point P is the center of the big circle, again. Point Q is the center of the small circle and point P is the center of the big circle. Okay, and we will also define a small r. A small r will be the radius of the small circle, and capital R will be defined as the radius of the big circle. Again, small r is the radius of the small circle, while capital R is the radius of the big circle. Okay, and we also know that this is a right angle and this is a straight line, so this is also must be a right angle, because of the rule that the sum of the angles on the upper side of any straight line equals to 180 degrees. So if this angle is 90 degrees, then the under angle must be equal also to 90 degrees in order to complete the sum to 180 degrees. And for the same reason, this is also a right angle, it equals to 90 degrees. Okay, and we also know that the small circle has small tangents. The first tangent to this circle is that this tangent is tangent to the circle at this point. Let's define this point as point S. Point S is the point of tangency between the tangent to the circle and the circle, or point S is the launch point between the tangent and the circle. And we also have the second tangent to this circle, and this tangent is tangent to the circle at this point. Let's define this point as point M. Again, point M is the launch point between the tangent to the circle and the circle, or the point of tangency between the tangent to the circle and the circle. Or we can say that it's also the point of contact between the tangent to the circle and the circle. And we have the third launch point between the tangent to the circle and the circle. Let's define this point as point Z. So we actually have three tangents to the small circle and three launch points between the tangent to the circle and the circle itself. The launch points are S, M, and Z. In the next step, we will draw three radiuses from the center of the circle to the launch points of those circles. Here we will draw the first radius that exits from the center of the circle and touches the circle at the launch point, that is point S. Okay, so this radius is drawn to the launch point. Actually, it touches the launch point, that is point S. And we'll also draw the second radius that exits from the center of the circle and touches the circle at the launch point at point M. So this is also the radius of the circle that is drawn to the launch point. And we will also draw the third radius of the circle that exits from the center of the circle and touches the circle exactly at the launch point. Okay, so we built three radiuses that exit from the center of the circle and touches the circle at the launch points, at point S and point M and point Z. And actually we have a rule number 1. Rule number 1 states that the tangent to the circle is perpendicular to the radius at the launch point. So I'll read rule number 1 again. Rule number 1 states that the tangent to the circle is perpendicular to the radius at the launch point. So actually we have here a radius that touches the launch point, that is to say it touches point S. Okay, so this radius is drawn to the launch point, that is point S. So according to rule number 1, the tangent is perpendicular to that radius, that is to say this angle is a right angle, it equals to 90 degrees. So if we draw a radius that is drawn to the launch point, then that radius will be perpendicular to its tangent. This radius is drawn to the launch point, therefore it is perpendicular to its tangent. And also here we have radius that is drawn to the launch point, therefore this radius is perpendicular to its tangent, that is to say this angle is a right angle, it equals to 90 degrees. And also we have the third radius that touches the launch point, therefore according to rule number 1 it is perpendicular to its tangent, that is to say this angle is 90 degrees and this angle is also 90 degrees. It is a right angle. Again, according to rule number 1, the tangent to the circle is perpendicular to the radius at the launch point. So any radius that is drawn to the launch point, then that radius will be perpendicular to its tangent. So this is a right angle, this is a right angle, and also this is a right angle because those three radiuses are drawn to the launch point. Actually they touch the launch points, therefore they are perpendicular to their tangents. Okay, and we will focus on quadrilateral QZMD. So on quadrilateral QZMD, has three right angles, 1, 2, 3. The sum of those angles is 90 degrees times 3 equals to 270 degrees. Okay, quadrilateral QZMD has 3 right angles, and the sum of those angles is 90 degrees times 3 is 270 degrees. And we have rule number 2 that states that the sum of the angles in a quadrilateral equals to 360 degrees. Okay, I will read rule number 2 again. According to rule number 2, the sum of the angles in a quadrilateral equals to 360 degrees. And especially the sum of the angles in quadrilateral QZMD must be equal to 360 degrees. So the sum of those 4 angles must be equal to 360 degrees. So we have 3 angles that the sum of them is 270 degrees. So if we will add the 4th angle, we will define the size of the 4th angle as y. So 270 degrees plus y, that is the size of the 4th angle, must be equal to 360 degrees. That is according to rule number 2 that states that the sum of the angles in a quadrilateral equals to 360 degrees. So according to rule number 2, the sum of the angles in quadrilateral QZMD must be equal to 360 degrees. That is to say, the sum of the three angles that equals to 270 degrees plus the sum plus the size of the 4th angle in total must be equal to 360 degrees. So here we will subtract from this equality 270 degrees, and we will get that the size of the 4th angle, that is y, must be equal to 360 degrees minus 270 degrees, that is 90 degrees. Okay, so we found out that the size of the 4th angle, that is this angle, must be a right angle. Okay, so we actually have 4 right angles in quadrilateral QZMD. Okay, so in quadrilateral QZMD, we have 4 right angles. Okay, we found out that in quadrilateral QZMD we have 4 right angles, and we have rule number 3 that states that if a quadrilateral has 4 right angles, then it is a rectangle. So I read rule number 3 again. According to rule number 3, if a quadrilateral has 4 right angles, then it is a rectangle. Okay, so our quadrilateral QZMD has 4 right angles. Therefore, according to rule number 3, quadrilateral QZMD is a rectangle according to rule number 3 because it has 4 right angles. Okay, quadrilateral QZMD is a rectangle because it has 4 right angles. Okay, 1, 2, 3, 4. Okay, and we have rule number 3 about rectangles, rule number 4 about rectangles. According to rule number 4, the opposite sides of a rectangle are equal to each other. The opposite sides of a rectangle are equal to each other. I will read rule number 4 again. According to rule number 4, the opposite sides of a rectangle are equal to each other. So actually, quadrilateral QZMD that is rectangle according to rule number 3 because it has 4 right angles. The opposite sides of this rectangle QZMD are equal to each other. That is to say, QZ equals to MD according to rule number 4. Okay, side QZ that is opposite to MD is equal to MD. QZ is opposite to MD, therefore QZ equals to MD according to rule number 4 that states that opposite sides of a rectangle are equal to each other. Rule number 4, okay, QZ equals to MD according to rule number 4 that states that the opposite sides of a rectangle are equal to each other. Okay, but we know that QZ equals to R, small r. It is the radius of the small circle. QZ is the radius of the small circle, that is to say it equals to small r. Okay, QZ equals to small r because it is the radius of the small circle. From this equality we can derive that MD equals to small r. Okay, MD equals to small r. Okay, so MD equals to small r. Okay, here MD equals to the radius of the small circle. So actually we will repeat on the same process on quadrilateral SQCM, this quadrilateral. Actually this quadrilateral SQCM has 3 right angles, 1, 2, 3. Therefore, according to rule number 2 that states that the sum of the angles in any quadrilateral equals to 360 degrees, the fourth angle must be equal also to 90 degrees. And so quadrilateral SQCM has 4 right angles, and therefore according to rule number 3 it is a rectangle, and according to rule number 4 the opposite sides of the rectangle are equal to each other, so SQ equals to CM and SQ equals to small r, so CM that equals to SQ also equals to small r. So CM also equals to small r. I write it down in the drawing that CM equals to small r, that is the radius of the small circle. Okay, Cm equals to small r. In the next step we will define Pm as x, that is to say Pm equals to x. So I write it here that Pm equals to x. Okay, if Pm equals to x according to our definition. So what is the value of Cp? Cp equals to Cm minus Mp. Again, Cp, this line segment equals to Cm minus Pm. I will write it down that Cp equals to Cm minus Pm. You can see it from the drawing, very simple. Cp equals to Cm minus Pm. But we know that Cm is the radius of the small circle. Cm equals to small r. Okay, Cm equals to small r. And Pm equals to x according to our definition. Okay, Pm equals to x. So we got that Cp equals to small r minus x. Okay, and in the next step we will calculate the radius of the big circle in 2 different ways. We know that the radius of the big circle equals to AP, because P is the center of the big circle. So we can write down equation number 1 that states that the radius of the big circle equals to AP, and we will also calculate the radius, the size of the radius of the big circle according to the second way, that we can say that the radius of the big circle also equals to PB. Okay, the radius of the big circle, equation number 2 states that the radius of the big circle equals to PB. Okay, so we will calculate the radius of the big circle in two different ways. The first way states that the radius of the big circle equals to AP. The radius of the big circle equals to AP. And the second way is that the radius of the big circle equals to PB. In total, AB equals to R plus R, to 2 times capital R. That is the diameter, AB is the diameter of the big circle. Okay, so we return to equation number 1. According to equation number 1, the radius of the big circle equals to AP. But what is the value of AP? It equals actually to AC plus CP again. AP equals to AC plus CP. Okay, AP equals to AC plus CP. Okay, but what is the value of AC? AC equals to 9 units. 9 units, it is given us in the question. And CP, what is the value of CP? We have already found out that the value of CP is R minus X. Okay, I write it down that the value of CP equals to small r minus x. Okay, so the radius of the big circle equals to AC plus CP. AC is 9 units and CP is small r minus x. So in total we found that the radius of the big circle equals to 9 plus small r minus x. Okay, the radius of the big circle according to equation number 1 equals to 9 plus small r minus x. Okay, that is the radius of the big circle according to equation number 1. But we have also equation number 2 that states that the radius of the big circle equals to PB. The radius of the big circle equals to PB because P is the center of the circle. But what is the value of PB? PB equals to PM plus MD plus DB. Again, PB equals to PM plus MD plus DB. Okay, or PB equals to PM plus MD plus DB. So PB equals to PM plus MD plus DB. Okay, so what is the value of PM? PM equals to X according to our definition. MD is the radius of the small circle. We found out that MD is the radius of the small circle. And DB equals to 4, it is given us in the question. So in total we got that the radius of the big circle equals to X plus small r plus 4. So I write it again. According to equation number 2, the radius of the big circle, the size of it equals to X plus R plus 4. Okay, so actually we have two different expressions for the same radius. This is expression number 1 in equation number 1, and we have expression number 2 in equation number 2 for the same radius. So of course expression number 1 equals to expression number 2 because we are talking about the same radius of the big circle, so we can compare equation number 1 to equation number 2 and we can say that capital R according to equation number 1 equals to capital 2 according to equation number 2. That will be equation number 3. According to equation number 3, capital R according to equation number 1, that is 9 plus small r minus x, equals to capital R according to equation number 2, that is x plus small r plus 4. Okay? Again, according to equation number 3, capital R according to equation number 1 equals to capital R according to equation number 2. So here we have R on this side of the equation and we have R on the other side of the equation, so we can cancel R. So what is left after we cancelled R is nine minus x equals to x plus 4. After we cancel R, we got this equality that states that 9 minus x equals to x plus 4. Here we can subtract 4 from this equality and we will get that nine minus 4 is 5, minus x equals to x. We got that 5 minus x equals to x. Here we will add x to this equality and we will get that 5 equals to 2x. So we got that 5 equals to 2x. Here we will divide this equality by 2 in order to get the value of x. And we will get that x equals to 2.5 units. 5 over 2 is 2.5. So we actually found out the value of x. X equals to 2.5 units. So we can substitute x in equation number 1 by 2.5 because x equals to 2.5 units. We have equation number 1 that states that the value of capital R is actually 9 plus R minus x. Okay, this is equation number 1 that states that capital R equals to 9 plus R minus x, and we have already found out that x equals to 2.5 units, so we can substitute x in equation number 1 by 2.5 units. Okay, we will get that R equals to 9 plus capital R equals to 9 to small r minus x. Instead of x, we will write 2.5. So we will get that r equals to 9 minus 2.5 is 6.5. So in total we got that r equals to 6.5. Capital R equals to 6.5 plus small r. Okay, we found out that capital R equals to 6.5 to small r and x equals to 2.5 units. Okay, in the next step I will present rule number 5 and we will implement rule number 5 in our two circles. According to rule number 5, if two circles have internal length between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. So I will read rule number 5 again. Rule number 5 states that if two circles have internal length between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. So actually rule number 5 states that if two circles touch each other internally, then the distance between their centers equals to the difference between the radius of the big circle minus the radius of the small circle. Okay, so we actually can implement rule number 5 in our circles because we have here two circles that have internal length between them at point N, that is to say they touch each other internally at point N. Therefore, according to rule number 5, the distance between their centers, that is to say the center of the small circle is at point Q and the center of the big circle the center of the big circle is at point P. Therefore, the distance between their centers is QP. This QP equals to the difference between the lengths of their radiuses. And the difference between the lengths of their radiuses are actually capital R minus small r. So in total, we can write down equation number 4 that states that the distance between the centers of those two circles, QP, equals to the difference between the radiuses of these circles, that is to say it is equal to capital R minus small r. Okay, so we got equation number 4 that states that QP, that is the distance between the centers of these two circles, QP, that is the distance between the centers of these two circles, is equal to capital R minus small r, that is to say it is equals to the big radius minus the small radius. Okay, so here we will add small r to this equation, and we will get that capital R equals to QP plus small r. Okay, and we also have equation number 1 that states that capital R equals to 6.5 plus small r. So actually we have two expressions for the same radius. So we can create equation number 5 that states that the radius according to expression number 1 equals to the radius according to expression number 4, because of the fact that we are talking of the same radius. So the expressions for those radiuses are equal to each other. So equation number 1 is equals to equation number 4 because they are the expressions for the same radiuses. Okay, so I write down that equation number 1 equals to equation number 4, that is to say capital R equals to capital R, and capital R according to equation number 1 equals to capital R according to equation number 4. Okay, so capital R according to equation number 1 is 6.5 plus small r equals to capital R according to equation number 4, that is QP plus small r. Okay, we got the equation number 5 that states that capital R according to equation number 1 equals to capital R according to equation number 4. So here we have R on this side of the equation and we have R on the other side of the equation, so we can cancel R. And after we cancel down, we will get that the value of QP is actually equals to 6.5 units. Okay, and we already found out that the value of X equals to 2.5 units. Okay, found out the values of QP and X. Okay, in the next step we will connect together points Q and P by a straight line. Okay, and actually we have here triangle QMP. Triangle QMP is a right triangle because angle QMP is a right angle. Okay, so in triangle QMP, that is a right triangle, we can implement the Pythagorean theorem. Okay, according to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, QP square equals to QM square plus PM square. Okay, according to the Pythagorean theorem, the square of the hypotenuse, that is QP square, equals to MP square plus QM square. Okay, according to the Pythagorean theorem, QP square equals to MP square plus QM square. QP square, the square of the hypotenuse, equals to MP square plus QM square. But we have already found out that QP equals to 6.5 units. So QP square is actually 6.5 square. Equals to MP square. MP or PM equals to X according to our definition, but we have already found out that the value of X is 2.5 units. So MP square is actually 2.5 square plus QM square. QM equals to the radius of the small circle, that is to say to small r, so QM square is r square. So in total we got that 6.5 square equals to 2.5 square plus r square. 6.5 square is 42.25 and 2.5 square is 6.25. So I'll write it down. So we got that 42.25 equals to 6.25 plus r square. Here we will subtract 6.25 from this equality, and we will get that 42.25 minus 6.25 is 36, equals to r square. Okay, 36 equals to r square. Here we will take a root out of this equality, and we will get that the radius of the small circle equals to the root of 36, and the root of 36 is 6, so we got that the radius of the small circle equals to 6 units. Okay, the radius of the small circle equals to 6 units. Okay, so now I will summarize the lecture. Actually, we wanted to find out the radius of this small circle. We know that those two circles have internal length between them at point N, and we also know that AB is the diameter of the big circle, and BD equals to 4 units, AC equals to 9 units, and also we know that this is a right angle, and this is also a right angle, and this small circle has 3 tangents, and this is the first tangent to the circle, and the launch point between the tangent and the circle is at point S. Here we have the second tangent to the circle, and the launch point between the tangent and the circle is at point M. And here we have the third tangent to this circle, and the launch point between the circle and its tangent is at point Z. Okay, so we actually, the next step, we draw 3 radiuses to the launch points, to points Z, S, and M. So those 3 radiuses that we draw touch the launch points S, M, and Z. Okay, so actually we have a rule that is rule number 1, and rule number 1 states that the tangent to the circle is perpendicular to the radius at the launch point. Okay, so here we have tangent to the circle and radius that is drawn to the launch point, to point S. Actually, this radius touches the launch point, that is to say, it touches point S. So therefore, according to rule number 1, this radius is perpendicular to its tangent, that is to say, this is a right angle. The same thing we have here, we have the radius that is drawn to the launch point. Therefore, according to rule number 1, this radius is perpendicular to its tangent. And here we also have the radius that is drawn to the launch point. This radius actually touches the launch point, that is point M. Therefore, according to rule number 1, this radius is perpendicular to its tangent, that is to say, this angle is 90 degrees and this angle is also 90 degrees. Okay, so we actually will focus on quadrilateral QZMD. This quadrilateral has 3 right angles, and the sum of those 3 right angles is 90 degrees times 3 is 270 degrees. And we have rule number 2 that states that the sum of the angles in a quadrilateral equals to 360 degrees. So, and especially in quadrilateral QZMD, the sum of its 4 angles must be equal to 360 degrees according to rule number 2. So actually the sum of the 3 angles, that is 270 degrees plus the size of the 4th angle, must be equal in total to 360 degrees according to rule number 2. Okay, so we created this equality, and from this equality we subtracted 270 degrees and we got the value of the 4th angle. The value of the 4th angle equals to 90 degrees. So the fourth angle is also a right angle. This angle is also a right angle. So we actually have quadrilateral QZMD with 4 right angles. And according to rule number 3, if a quadrilateral has 4 right angles, then it is a rectangle. So quadrilateral QZMD that has 4 right angles is a rectangle according to rule number 3. So this is a rectangle. Okay? But we also have rule number 4 that states that according to rule number 4, the opposite sides of a rectangle are equal to each other. Okay? So the opposite sides in rectangle QZ and MD are equal to each other. That is to say QZ equals to MD, because QZ is opposite to MD, so QZ equals to MD according to rule number 4. Okay, we have the equality that states that QZ equals to MD according to rule number 4. But we know that QZ is the radius of the small circle. Okay, we can write here that QZ equals to small r, that is the radius of the small circle. So we have this equality, and from this equality, MD that equals to QZ that equals to small r, we can derive the equality that MD equals to small r. So MD equals to the radius of the small circle. MD equals to the radius of the same circle. And we have, actually we repeated on the same process for the quadrilateral SQCM, because it has 3 right angles. So the fourth angle must be equal also to 90 degrees, according to rule number 2 that the sum of the angles in a quadrilateral equals to 360 degrees. So if it has 3 angles that equals to 270 degrees, then the fourth angle must be complete the sum of the 3 angles, the total sum of the 4 angles to 360 degrees. Therefore, the fourth angle must be equal to 90 degrees in order to complete the sum of the 4 angles to 360 degrees. So this is a right angle. So quadrilateral SQCM has 4 right angles, and therefore, according to rule number 3, quadrilateral SQCM is a rectangle, and according to rule number 4, that the opposite sides of the rectangle are equal to each other, SQ equals to CM. Okay, but SQ equals to small r. So CM that equals to SQ must be also equal to small r. So CM equals to small r. Okay, so we got that MD equals to small r and CM also equals to small r. Then we defined PM as x, that is to say PM equals to x, and CP actually equals to CM minus PM, that is to say CP equals to CM, that is small r, minus PM, that is x, so CP equals to r minus x. And then we actually created 2 equations for the radius of the big circle. The first equation states that the radius of the big circle equals to AP, capital R equals to AP, capital R equals to AP, but what is the value of AP? AP equals to AC plus CP. and AC equals to 9 units, and CP equals to small r minus x. So in total, AP equals to 9 plus r minus x. That is equation number 1. And we have also equation number 2 that states that capital R equals to PB. Capital R equals to PB because P is the center of the circle. But what is PB? PB equals to PM plus MD plus DB. That is to say PB equals to PM, that is x, plus MD, that is small r, and BD, that is 4. So in total, capital R equals to x plus small r plus 4. And we have equation number 1 that states that capital R equals to 9 plus small r minus x. So we have two expressions for the same radius. So we can compare those two expressions because we are talking about the same radius. So we can state equation number 3 that create equation number 3 that states that capital R according to equation number 1 equals to capital R according to equation number 4, according to equation number 2. Capital R according to equation number 1 equals to capital R according to equation number 2. Okay, that is equation number 3. And from equation number 3 we got the value of x. We found out that x equals to 2.5 units. And so we can substitute x by 2.5 units in equation number 1. So we got that capital R equals to 6.5 plus small r. Okay, and we know that x equals to 2.5 units. Then I presented equation rule number 5, and we implemented rule number 5 in our two circles. Rule number 5 states that if two circles have interval lunge between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. So if two circles touch each other internally, then the distance between their centers is equal to the difference between the radiuses. That is to say, it will be equal to the radius of the big circle minus the radius of the small circle. Okay, so we can implement rule number 5 in our two circles because we have here two circles that touch each other internally or that have internal lunge between them at point N. Therefore, according to rule number 5, the distance between the center, that is QP, will be equal to capital R minus small r. That is the difference between the radiuses. Okay, QP equals to capital R minus small r. So from this equation we got that capital R equals to QP plus small r. And we have equation number 1 that states that capital R equals to 6.5 plus small r. So we have two expressions for the same radius, so we can compare equation number 1 to equation number 4 and create equation number 5 that states that capital R according to equation number 1 equals to capital R according to equation number 4. And we got that the value of QP is 6.5 units, and we already found out that x equals to 2.5 units. Okay, so then we connected together points Q and P by a straight line, and we have the green triangle that is a right triangle because of the fact that angle QMP is a right angle. So triangle QMP is a right triangle, so we can implement the Pythagorean theorem in triangle QMP, the green right triangle QMP. According to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, QP square equals to QM square plus PM square, or QP square equals to MP square plus QM square, and we know that QP equals to 6.5 units and MP that equals to X according to our definition is equals to 2.5 units, and QP equals to 6.5 units. So the only missing variable here is the radius of the small circle. So we put the data inside this equality and we got that the radius of the small circle equals to 6 units. Again, the radius, that is to say small r, of this small circle equals to 6 units. Okay, thank you very much.